Welcome to this ISAC webinar. We are going to talk about Space Elevator 101. Essentially, how do we build one and why do we build one? But first, I'd like to remind you that our website, www.isac.org, has a wealth of body of knowledge. We have over 800 citations. We have 12 study reports. We have lots of ties to websites and videos, et cetera, et cetera. Very worthwhile going there to answer your own questions. But today we're going to talk about the current space elevator. Now, I call that the modern day space elevator. We came up with that name when we recognized that we have a material that should work for the space elevator tether. Single crystal graphene is developing rapidly, and we really have hopes it'll be long enough and strong enough and exactly what we need. So what we're going to do is go fast through these charts because they'll be available to you afterwards, and you can go through the details at that point. But what I'd like you to do is focus on the concept and the ideas that are being brought up, because this is preliminary. This is what is a space elevator, and even more basic, why a space elevator? So we've got a modern day space elevator. We've come up with the term green road to space because we don't burn anything in the atmosphere. We raise everything with electricity, and we also enable missions that can significantly help our atmosphere, even stop global warming, is one claim. So we're ready to start engineering, and we want to join rockets as a collaborative approach to space. We call that the dual space access architecture. The real kicker is we move massive amounts of cargo. We'll show you some numbers here that'll just blow your socks off compared to our history. But first, let's talk about dreams. Dreams, they're great. We've had these dreams of going to space a long time, but we're actually talking about going and moving off planet. Mr. Musk, Mr. Bezos, et cetera, et cetera. You can see there's a station on Mars there with Mr. Musk. We've got the lunar village. We've got Mr. Bezos standing next to his lunar lander. We've got the NASA Space Launch Systems, and we've got the L5 Society vision of a rotating cylinder up by the moon, and it'll be 4 miles long and 1 mile in diameter, or something like that, big. But nobody ever asks the silly question, how much does it weigh? And the reason they don't ask that question is because it's a bad answer. There's lots of mass that's required for each one of those dreams. What I've done here is shown a few of them. Space solar power to stop global warming, 3 million tons to GEO. Ooh, bummer. Moon Village has got to be 500,000. Space Colony, 1 million tons to Mars. And the L5 Society, it took me like 3 months to figure out what the mass was, because I did not want to talk about mass to the L5 location. But I finally got a number at 10,500,000 tons. Now, it turns out we've only put 26,000 tons into orbit, and it took me about 6 weeks to figure out how many satellites were launched and how much the satellites weighed, et cetera, et cetera, et cetera. 26,000 tons. Remember that number. We're going to talk about mass during this discussion today. So the dreamers have big dreams, and the one on the left in the image is our dual space access dream, where we work collaboratively with the rockets. They move things through the radiation belt rapidly like people, and we move the heavy lifting. Okay, the space elevator vision. We basically are the green road to space that's routine, safe, inexpensive, daily, and environmentally neutral. We're going to join the rocket guys in dual space architecture and leverage their experience and their strengths. And then we're going to leverage our strengths. The bottom line is we move massive amounts of cargo in a routine manner, just like a train setup. So why are we doing this? Well, the first question you ask when you start talking about space elevators, why the heck should we do that? The bottom line is we escape gravity. We beat gravity. Okay, well, let's talk about some specifics, the transformational strengths. The first is daily. Okay, routinely, safely. And how do you do that? Well, you make a permanent space transportation infrastructure. So it's like train tracks to space. Massive movements. I'm going to show you some more charts about 30,000 tons per year for us during the early years. High velocity at the apex anchor, we're going 7.76 kilometers per second. When we release from there, we go to Mars in as short as 61 days. Every day we can release toward Mars. Now, some of them are longer than 61 days. The average is about 80, 85, somewhere around there. Some trips are 400 days. Got to go all the way around the sun and stuff like that. But the point is we release every day. There's no 26-month wait. The green road to space is I've talked about, and it's very, very important that we do not affect the atmosphere as we go through it. But the kicker, and most people don't know this, it's only been brought out the last 2 years by a pair of authors, and Kevin Barry and Eduardo, have they come up with transforming the economics. We no longer talk dollars per kilogram. That's launch people talk. We talk strategic investment, economic development. Think a bridge going across a river and the city or town you develop on the other side. That's what we do. And then, of course, we've got the dimension complexity reduction. My wife came up with this one in that we don't do shake, rattle, and roll, and we're not restricted to fairing on the top of a rocket. Okay, we've done a lot of studies. Please go to our website and look at these. The Green Road to Space was the recent one we've completed, but we also have one almost completed, which is a tether and the climber interface study, looking at the material and how a tether climber would grip it. We also have one just started, which is dual space access architecture. How are we going to work with rockets? That's a very good topic. We're going to have fun with that. In addition, we've got 2 International Academy of Astronautics studies, and they essentially looked at the technology readiness and came up with a conclusion. We're ready to go ahead. Obayashi did a major study and defined the space elevator for 100 metric ton tether climbers. Brilliant design. Okay, here's our book. I just show this because it's important to reflect that we have done 12 studies. Each is about 18 months long. A bunch of experts work on it, and we write it up, and then we have a study. Here are the 2 International Academy of Astronautics studies. They came up with the answer that the preliminary technical readiness assessment has been accomplished, and we're ready to proceed. Okay. Remember, back to massive movement. We've basically put 26,000 tons. This chart says 22,000. I added up all the details here. But basically, we've only put 26,000 tons into low Earth orbit mostly. And we're planning on putting 30,000 tons to GEO and beyond on our first operational year when we're at initial operations. 30,000 tons versus less than that in 60-some years. And then when we get to full operational capability, 170,000 tons. Now think about that a little bit. Mr. Musk wants 1 million tons to Mars. We can do it in like 6 or 7 years. Once we get operational, it'll take a little while to get to that level, but once we get fully operational, we'll be able to move massive cargo. Okay, humanity's needs for movement off planet. There are a lot of things we need. And these are the strengths of an inherent permanent infrastructure where you have tracks in the road, so to speak, but they're vertical tracks. So we've got permanent capability, routine, 24/7, 365, 50 years, low cost, et cetera, et cetera, et cetera. Think train tracks and you think about what we can do. The revolution is coming because we're going to also, in addition to moving stuff up, we're going to enhance them with velocity. So when they release, they're going tremendous velocities. We bring it up to geosynchronous and they're going fast enough to stay in that orbit right next to their location. In addition, you go higher and you can release at 100,000 kilometers where our current apex anchor is and go to Mars in 61 days, as short as 61 days. If you go all the way to the top, if you build a long space elevator, we can escape the solar system without rocket fuel. That's the type of velocities we're talking about. Remarkable. Okay, we did a great study with Arizona State University and came to some conclusions, but the one with respect to Mars was brilliant. We can go every day to Mars. Remember, rockets have to wait every 26 months to get a planet alignment. We can go as fast as 61 days. Well, some trips, they're not aligned quite right, so it's 400 days. But if you're sending hammers and nails, who cares? It's a logistician scheduling problem. But we move massive amounts of cargo. And that's the kicker. We want to work with rockets. We want to do the heavy lifting. Okay, here's just a quick case on the Arizona State University where we go from the Earth to Mars. We cut the corner. We don't do the Hohmann transfer, which is minimum energy. We go fast. And so you can see that we could do it in 61 days, or if you go around and catch it on the other side, then it might be, 90 days or something like that. The average is somewhere around 85 or 90, something like that. Okay, now here's a brilliant idea that came up during our study. Let's have a schedule. Let's have a bus schedule. Heck, we could have a bus schedule to Mars. Tuesday, we send it, it'll get there in 61 days. Thursday, we miss the opportunity, it's going to take 400 days, but we release every day. So you send the pizza on the 61 days and you send the hammer and nails on the long one. So it's a bus schedule. Think about that. That's going back to trains transportation, airplane transportation. It's a transportation strength. Our idea is that we develop 6 space elevators. We develop in pairs because what we want to do is we really want to have a principal and a backup in case, the principal gets in trouble. Or we want to have 2 going up. That's where the money is early on, taking stuff up. And then when we want to bring stuff back, we want to have 1 up, 1 down. So the idea is 3 pairs, Pacific, Atlantic, and Indian Oceans based. Okay, now the part about how you do this. Well, the first idea is you run a string all the way up to 100,000 kilometers long, and then take little climbers up it and build the ribbon up 1 stage at a time. That's the concept that's been around for years, but you make it 100,000 kilometers long. The centrifugal force at the end, taking the apex anchor and tossing it outward, keeps the tether tension and keeps it stable. So it's a very inherently stable tether that you climb on. And if you look at the lower right in that image, we've got the tether outside of the bow shock. This is remarkable. 100,000 kilometer is a long ways. We understand that, but it's remarkable. Now, take your image and rotate that tether around 24 hours, and it goes in and out of the bow shaft and goes to the plasma sheath. So the magnetic fields are changing all along. It could be a strength or it could be a hazard. We don't know yet. We're working that. Okay, how do we do it? It's very simple. What we do is we take our tether up to geosynchronous and we spool it down. And to keep the center of mass at geosynchronous, you move the apex anchor up. And then you spool down, and you grab it at the ocean and wrap it around your big anchor there at the bottom. And you let the top, the apex anchor, go a little bit further out, getting extra pull to make it extra stiff and extra strong. And then what you do is you take little tether climbers and you climb up the rope and you build up the tether. So we have an initial tether and then we build it up to an operational tether. So that's all it is. And some guys calculated all that as 276 trips or some number like that. There's a lot to be done in our design, but that's the early concept. And so we end up with a tether 1 meter wide, 100,000 kilometers long, strong enough to move 170,000 tons per year. Okay, we sat down with the Japanese, who are very, very big time in space elevators. We sat down with the Europeans, who have had some good tether competitions over there. And we sat down with all the Americans and we came up with a terminology so that we could actually talk amongst ourselves. Earth port, we've got apex anchor, we've got geo nodes, we've got all kinds of terms, but the idea is we've developed the concept pretty well. Here are 3 little tether climbers. The first one on the left is your deployment. You see the big roll of tether down at the bottom there. You run the tether down and you go up with your big mass, and you can see a lot of fuel to keep it stable and all that kind of stuff during all the deployment, get it there and all that kind of jazz. Then we have the baseline tether climber in the middle. That's the concept. We're at the concept level now. We're not designing actual thing. We need some customers to give us some customer requirements. And then the climber that's going to build up the tether is on the right. You can see the spare cable there over to the right. Okay, here's just a concept. We've got lots of concept. A whole bunch of people have ideas. Just one concept on the tether climber. Now we're looking at the tether material. When we started, the carbon nanotube was the idea, and it would beat all the normal materials in strength to weight. So it would beat all these normal things and it would be up there at that top level. But the carbon nanotubes has been overtaken by events. We're now looking at graphene, and the graphene is a remarkable material and will be ready for us, as promised by a member of our board of directors. And he's working in the industry to come up with single crystal graphene. Okay, the answer is it's strong enough and it'll be long enough, so it is our material at this time. Idea is the tether would look something like that going up, and we would have a bunch of strands and everything else. We're not really sure how we're going to weave it or anything else. We've got a lot of thinking and designing to do there. Now, this is important. Graphene was discovered about 14 years ago. A Nobel Prize was awarded to the University of Manchester and some gentlemen there. And now we have production of graphene, 100,000 meters squared right now. Now, this is not the graphene that's good enough for our tether. It's called polycrystalline, so it's one notch down below what we need. But the key is the process to develop a continuous stream of material is the same process. So we have the same process and we would just keep doing. And so we're working on how do we take single crystal graphene and get to a production line. That's where we're at today. Here's a good look at what it would be like. We'd have one continuous layer of tether, 100,000 kilometers long, come off a machine like the one we just saw. And the question is, how much does it weigh? What's the mass? Well, how about 77 kilograms? It's very lightweight and extremely strong. So we're really cheering on this particular activity. Here's a picture of our floating operations platform at our Earthport. It'd just be one of the buildings where the people are working at. They have the opera center in there and all that kind of stuff, as well as a swimming pool and tennis court, maybe some fishing and stuff like that. But anyway, the real kicker is we're along the way in designing the initial concepts. Here's the concept of what we would do with the two tethers, one up, one down, one up, one back up, or two up to make cash. So we have the Earthport, which will be very busy loading and unloading. We'll have the GeoNode, where we have a lot of business for all the geosynchronous communication satellites, weather satellites, et cetera, et cetera. And then we have the release point up at the apex anchor where we'll be sending things. Now remember, it's only 14 hours to the moon. So we have a rapid transit to the moon. We could have all kinds of supplies and do a just-in-time supply process, logistics process to supply people on the moon. Now, where are we? We're in the process of entering engineering validation. We need to start testing our concepts. That's where we're at. Then after we test our concepts and come up with the designs, then we got to build them and test our different segments. And then we have mission up. So we're in the second blue box is the way I like to think of it. We're beyond the technology assessment phase. We're into the process. Here's a schedule, pick any schedule you want, but it's basically 2037 is when we should be operational. So that's what we're looking for. Okay, dual space access. I talked about this a little bit. What we really want to do is be collaborative, cooperative with rockets because they have tremendous strengths. We need rockets to land on any planets or moon. We need rockets to rendezvous. We need rockets all over the place. But let's beat the gravity well. Let's get out of the Earth gravity well with the heavy lifter called space elevators. That's what we need to do. We need to minimize the rocket equation limitations. Okay, so why are we doing space elevators? The answer is simple, we must. If we want to fulfill the dreams of many, and one of which is to save our atmosphere, it would really, really be good to have space elevators. So literally, we in the space elevator business believe that we must do space elevators. So we're charging ahead, trying to develop space elevators. They're a simple, elegant solution to the rocket equation. And if you don't beat the rocket equation, you're not going to have a robust movement off planet. So we must do space elevators. Thank you very much for your time. And the definition of what a space elevator is and where we're going is exciting. And please join ISIC and maybe sign up for the newsletter. But ISIC is an organization that's volunteer and trying to move the technology and concepts forward.